Good morning, everyone. We'll pick up from where we left off yesterday and have a look at how we can use this these Euler-Lagrange equations that we derived from a variational principle in order to actually make some useful calculations. So let me just remind you very briefly what we did. We proved that if you started out with Hamilton's principle, which is a global principle, you can actually derive Lagrange's equations. And to express this mathematically, we used this quantity, which is the action of the system. This is the Lagrangian. And we saw that Hamilton's principle stated that the actual path that any system will take through configuration space, which was always spanned by the different generalized coordinate axes, would be such that this action should have an extremal value. And we saw that that would actually lead up to Lagrange's equations. And towards the very end of the lecture, we put this in a slightly different notation and wrote And we wrote that if you consider this integral over some function of y prime, which denotes derivation with respect to x instead of t, this integral will have a stationary value if the following condition is satisfied. That was the last thing we did, basically. And these are the Euler-Lagrange equations. So I promised you that we could find some use for this practically. Well, this would be of use anytime we have some quantity which can be written like this, which is a quite general form. It's an integral over a function that we want to find an extremal value for. And this could have applications even outside of physics, economics, geography, whatever. Whenever you have a quantity which can be written like this, and you want to find the extremal value of this quantity, and this can represent anything. It could be a quantity in economics, for instance. Well, what you need to do is to find this condition. You have to write down this condition for the relevant function. So let's take an example of that. And the example is to find the minimum area of the following object. So imagine we have three-dimensional space and we have some object here. And let's say that we can obtain this object by first fixing 2 points in the xy plane, x1, y1, and x2, y2. And then just take the curve between these 2 points and revolve it around the y-axis. So you get this object. Okay, and the task is now as follows. We want to find the curve that takes us between this point 1 and point 2, which will give the minimum surface area of this object. We want to find the curve joining these 2 points, which gives the minimum area of the object. So this could be a practical situation. Say you want to fit some object onto a certain part of an oil platform, and you need to make sure that it satisfies certain dimensional requirements. So this could be an actual engineering task. Okay, so how do we go about to find the curve which gives the minimum area? Well, we can actually use the Euler-Lagrange equations. Imagine we take just a segment here of the object, and the width here is ds, it's just an infinitesimal width. Then the area of this sort of cylindrical segment is just 2 pi x ds. Now, ds can be written like this, expressed in terms of the infinitesimal quantities dx and dy. So it means that using this, I can rewrite this expression in terms of dx rather than ds, where I've now introduced y prime, which is dy dx. Okay, so if the area of this stripe is given by this expression, then the total surface area of this object should be obtainable by integrating this expression here from x1 to x2. And as you can see, this integrand actually has precisely this form. It's a function of x and y prime. There's no dependency on y, but that's okay. This function should just in general, it can in general be a function of y, y prime, and x. But if there's no y dependence, that's okay. So we have this. Okay, so we've identified the function f, and then we can just start with the machinery here and compute the derivatives. Okay, so first off, there's no dependence on y, so the partial derivative with respect to y is 0. There is a dependence on y prime, however. Which looks like this. And so let's plug this into Euler Lagrange equation over here, and we get this. And that may look like a somewhat hairy equation, but we can solve it actually. You see that it's written like a total derivative of something which is equal to 0. So this something has to be a constant. Now let's call this constant a. So I can rewrite this like so. And this equation is equivalent to this. And now we're in a much better position. This looks more reasonable. So we have the derivative of y with respect to x is equal to some rather well-behaved function here. So it follows that y has to be the integral over this equation. And I'm not attaching any limits for now, so we have to keep in mind to bring an undetermined constant along with us. This is a standard integral, which you can look up in any mathematical collection of formula. And it's equal to the inverse of hyperbolic cosine with an argument x over a, and here's b, the undetermined constant, since we haven't specified any limits on this integral. So that's one way of writing it. Another way, if you prefer to work with conventional hyperbolic cosines instead of their inverse, is to rewrite this equation expressed as x equals a function of y. So with proper initial conditions or boundary conditions, so that we know a and b, this is a solution for the curve which gives the minimum surface area of the object. So I've said that it's the minimum. Can I be sure about that? If you think back to the Euler-Lagrange equations, can someone state with words what are they a condition for? Yep.
Extremal values?
Yes, exactly. So let me just repeat that. Extremal values for the video recording. And extremal values include minima and maxima. But I'm standing here and trying to convince you that this actually represents a minimum in the surface area. Do you buy that? Why?
Cannot have a maximum area.
Because?
Because you can always expand the area a little more.
Exactly. So what he says is that you cannot have a maximum area because you can always expand the object and make it even bigger, and hence increasing the surface area. So whenever you do physics, the mathematics is all good and well, but you also have to keep in mind your sort of intuition. I'm going to get killed for saying this, but this is a major difference between mathematicians and physicists. You can't just take the result and look at it and say, okay, this is fine. You also have to keep in mind what's physically going on, right? So exactly as you say, we can be sure that this is a minimum because there is no maximum. You can always increase the curve, right? Just dragging the object further and further. So we can, with a good conscience, state that this is the minimum. We'll have a crack at one more example. Which is a truly classical problem in this kind of mechanical physics. It's a challenge to even spell this, but it's known as the brachistochrone problem. What brachistochrone means is essentially something which refers to finding the minimum time required. The problem essentially looks like this. Imagine we're working in a plane, the xy plane. We have a particle which starts out in position 1 and ends up in position 2 later, at some later time t. And gravitation works in the positive y direction. The brachistochrone problem is as follows. Find the curve between 1 and 2 so that the time required by the particle to travel between 1 and 2 is minimal. Now, perhaps your gut feeling would be to say, okay, this is a straight line. Well, that would be the shortest distance, but it's not necessarily the shortest path which gives the minimum time that the particle requires to travel between them. This is due to gravity here. So you could imagine, for instance, that instead of a straight line, if you have some curve which goes like this, it allows the particle to accelerate faster by traveling down here and then just swooping in here and spending actually a shorter amount of time than if it were forced to move in a straight path. So this is different from the shortest distance required. So it's not equal to shortest distance. Okay. So first of all, we have to identify the function which we're trying to find the minimum of. And this is t12, the time required to travel from point 1 to point 2. Since we're interested in finding the path or the curve linking 1 and 2, which gives the minimum time, it's natural to express t12 in terms of an integral over infinitesimal lengths, ds. And time is equal to dt is ds over v, so we get this expression. All right, well, we have energy conservation here. There are no explicitly time-dependent forces or potentials in the picture, so energy is conserved. We just have one conservative force. So we just choose basically the reference level of potential here, so that the particle has potential energy to begin with, and everything is converted into kinetic energy. And by writing the conservation of energy like this, I'm actually making an assumption. Can you see what it is? I'm making an assumption about the velocity of the particle. Yes, that's true. It's non-relativistic. I have one more assumption. Okay, a clue. For energy conservation, I'm equating the energy before in point 1 with the energy after in point 2. So I'm saying kinetic energy plus potential energy. Yes?
Start with no velocity.
Yes. The velocity in point 1 to begin with is 0. So I'm basically saying the particle only has potential energy to begin with at point 1, and everything is converted into kinetic energy at point 2. Okay, using this equation, I get the following for the velocity. Inserting it into the expression for T12, I get this. This is just the rewriting of ds, similarly to what I did in the previous example. And this is the velocity. Which means I can identify the function f here in the integrand, like this. Now, this is slightly different from the previous example, because now we have no dependence on x, but we have a dependence on y, which we did not have in the first example of the minimum area. Okay, next step, find the Euler-Lagrange equations. And we get this. So we can already see that it's going to be more complicated than the previous example, because in the previous example we were fortunate enough to have this 0. So we only had the x derivative of this expression. But now we have two terms. By using these results, the Euler-Lagrange equation becomes this. Now this looks like a challenge. How can we possibly solve for y from this expression? It's basically a nonlinear equation in y prime and y. Well, let's have a go at it at least, so we can say we tried. And let's start off with this term first, the second term. So we have to we have to differentiate this expression with respect to x. You should get something like this by deriving each term or differentiating each term with respect to x. Well, this has a common prefactor. So we can write this we get this. Now, I'm going to skip a few steps in order to make the derivation a little bit shorter, but it's shown in the compendium that you can take this expression and simplify it to the following. You can actually cancel some terms here. This, in turn, can actually be rewritten as the derivative of a logarithm, the natural logarithm. So this can be written as the total derivative with respect to x of this expression. So keep in mind that, for instance, the derivative of the logarithm of x is 1 over x. So by doing that, you can actually achieve to get this expression. Well, if this derivative is 0, it means that this term here inside the parentheses has to be a constant. And if the logarithm of this term here inside the square brackets is a constant, then the square brackets themselves also have to be a constant. So what we find is that this term has to be a constant. And that's a whole lot simpler. Now, it's convenient to name this constant 2k. Because if we do so, we can actually represent x and y in terms of an independent parameter theta in the following way. So we parameterize x and y. We write them like this. And you can check now that if x is equal to this and y is equal to this, if you insert these transformation equations into this one, you will see that it's satisfied. So the behavior of the particle in terms of this theta should be something like this. You see that if we start out at 0, then x is 0, starting at point 1, and y is also 0. It's starting off in the orgo of the coordinate plane. Then as you increase theta, it will take this parabolic-like curve down to the second point. So you see that the path that the particle takes to get the minimum time in order to travel between 1 and 2 is actually far from a straight line. It has this form. So the example with the object and the minimum surface area and this brachistochrone problem serve to illustrate how you can use the Euler-Lagrange equations for practical purposes and actually make statements about the extremal values of some quantity which you want to find the extremal value of. For instance, the minimum. And again, we can be sure that this is a minimum because we can always find a path that will increase the time that it takes for the particle to travel from 1 to 2. Okay, we're going to move on to having a look at Hamilton's principle for a different type of system that we've been doing so far. So far, we've had a look at Hamilton's principle for holonomic systems. Now, for holonomic systems, we have a special form for the constraints. We know that the constraints can be written in the form of a function of the coordinates and possibly time is equal to 0. For non-holonomic systems, we cannot do this any longer. The example we used, I think, was, for instance, a car driving on a hill, in which case the position of the car must be equal to or greater than the radius of the hill if the hill is circular. So then you get an inequality sign in the constraint of the system. So it's no longer holonomic. So the question is then, if we have a non-holonomic system where the constraints must be written with these inequality signs, what happens with Hamilton's principle? Can we still use it? So, like I said, so far, we've considered holonomic constraints like this. So in that case, with j holonomic constraints, we could introduce small n equals 3 times large n minus j generalized coordinates, which would be independent, where the constraints would automatically have been taken into account. And let me just remind you of what Hamilton's principle gave for this situation. So Hamilton's principle, written like this, we showed would give us this expression, which for independent generalized coordinates qk gave us these Lagrange equations. So the question is then, how does this change if you have non-holonomic systems? And the main point here is that for non-holonomic systems, all of these virtual variations, del qk, are not independent anymore. Right, so we'll take 15 minutes break.